All right, here we are in section 7.3. The section title is partial fractions. This is a bit tougher, and these notes are definitely going to take us a little longer to get through, so let me jump right in. Our objective is to recognize what we call partial fraction decompositions of rational expressions. A partial fraction decomposition, and recognize them, and then also find partial fraction decompositions of rational functions. Basically, the long and the short of this is that we are trying to break fractions down into smaller fractions. We've done some of this with basic numbers before, but now we're doing it with rational expressions. Let me start out with these first couple of examples where it says solve each rational equation. In order to be able to do any of this partial fraction decomposition stuff, we have to remember and know how to solve rational equations. So something like this you would have seen in Algebra 2, you may have even seen it in Algebra 1, something like this, the first example, but we're adding 1 over x to 4 over x plus 1, supposed to be equal to 6. Most students will look at that and go, okay, well, you're adding two fractions, you've got to first combine the two fractions into one, and then maybe multiply by the denominator and so on. I'm going to say the easiest strategy is to take the entire fraction and multiply by the common denominator of each fraction. Notice that this 6 is technically 6 over 1, so if you want to write it as a fraction, it is still a fraction. It's a rational value, 6 over 1. The common denominator here is the product of all three denominators, the product of x plus 1, and of course 1. And so that product is x times x plus 1. All right? And what happens is I'm going to multiply this common denominator into all three fractions, here, here, and here. So I get, the original statement was 1 over x times x plus 1. If that confuses you, you can put this over 1 also. It's technically x over x plus 1, or x times x plus 1 all over 1, plus 4 over x plus 1 times x plus 1 over 1. And it equals 6, or 6 over 1 times, in fact, I'm not going to put it over 1, I'm just going to leave it as 6. 6 times x plus 1. All right? So as we do this, it's multiplied into all three pieces. And you'll see that when multiplied, for example, the x in this fraction cancels the x in the numerator, and we're left with just x plus 1, the x plus 1 times 1. In the second fraction, the x plus 1 on the bottom cancels with, I just realized I'm using a different color, let me switch, cancels with the x plus 1 in the numerator, and we're left with 4 times x. And then that equals what is technically 6x squared plus 6x. And so by multiplying by the common denominator here, we have essentially cleared all fractions out, and we're left with just a simple statement with no fractions in it. And that's our goal. We want to try to make this as easy as possible, where it just has the fractions, or it just has the single expression. I just realized that maybe I'm jumping ahead of myself a little bit. Maybe it would be easier if I showed that technically what happens is we have, when the x's cancel, we have 1 times the x plus 1, and then we have the 4 times the x left over there, and then we still have the 6 times the x plus 1 here. All right, when those things canceled. All right, so rolling ahead, now our job is still, we're trying to solve the equation, so we need to find the value of x that makes the equation true. We're still trying to isolate x and get it by itself. So what I'm going to do is I'm going to move everything to the right side and set this thing equal to 0. So I have 6x squared. I've got 5x on the left. That's going to subtract and make 1x on the right when it subtracts from the 6 that's there. and then the minus 1. And now we're left with a quadratic expression, and the quadratic will factor, factoring again, a key strategy. It's one of those techniques that we got to know how to do. If I factor this, I'll distribute the x here and here. I know that the only factors of 1 are 1, so these got to be 1 and 1. And I'm trying to get to 1x in the middle, so I don't want 6 and 1. If I use 3 and 2, then if I let the 3x be positive and the 2x be negative when multiplied, and double check this, positive 3 times positive 1, right? The outside product here would give us positive 3x. Negative 1 times positive 2 is negative 2x for the inside product. And when you add positive 3x and negative 2x, you get positive 1x. When you multiply 3x and 2x, you get to 6x squared. All right? So that is the correct factoring. And so we set each factor equal to 0, and we solve. We've got x equals 1/3 for the first expression, and x equals negative 1/2 for the second expression. And so those are our two answers. Negative 1/2, positive 1/3. Now, I left the domain off here, and I probably should have done that first, but let's talk about that now. If I go back to the original statement, this is my original expression. I really should be concerned about which values of x are allowed at all. Which values of x could be plugged into this expression. And when we consider the denominators, we cannot let x be 0, and we cannot let x be negative 1. If x is 0, we've got division by 0 here. If x is negative 1, we've got division by 0 here. So our domain is any number except, I'll say real quick, all real numbers, but x cannot be 0 or negative 1, is not equal to. Now that's not exactly the formal way to write this. If I was writing it formally, I would do it in interval notation. So that's negative infinity to negative 1, negative 1 to 0, and 0 to infinity. That would be the correct way to write that domain if I had to. All right, let's, and we verify neither of the values we found, negative 1/2 or positive 1/3, are excluded. And so these two answers are both good. We'll leave them. Moving on, number 2. Number 2, we're given a quadratic in the denominator here. So the first step would be to factor that and write this in factored form. So I'm going to start out 12 over, if I factor x squared minus 4, I get x plus 2 times x minus 2. All right? And then I'm adding that to what is 3 over 2 minus x. But notice 2 minus x is the opposite of x minus 2. In 2 minus x, the 2 is positive and the x is negative. In x minus 2, the x is positive and the 2 is negative. So if I just negate that, if I call this the negative of x minus 2, then if I were to distribute that negative again, I would end up back where I started, 2 minus x, right? So I'm going to write it that way so that this factor matches this factor. So the x minus 2 matches the x minus 2 here. It makes this a little easier. If I can get away with having less factors to deal with, I'm going to do it, and that's certainly what's happened here. All right. Not only that, but I don't like that negative in the bottom. Remember, for example, negative a over b is the same as positive a over negative b. They're the same thing. So I have the option to pull this negative up top, which is what I'm going to do. I'm going to move this negative here, and I'm going to put it on the numerator so that the 3 is negative. And now this equation is a little bit easier for me to handle. And of course, all that equals negative 1. All right? So before I go any further, let's stop and do the domain. The domain here is any number except what will cause division by 0. So if we look carefully, we've got positive 2 would make this expression equal 0, and this expression equal 0, and negative 2 would make this expression equal 0. So we have to exclude, I'm going to say all real numbers. My thing is going crazy here. I'm going to say all real numbers, there we go, except x cannot be positive or negative 2. And if I was writing that in interval notation, it would be negative infinity to negative 2, negative 2 to 2, positive 2 to infinity. All right, so I just have to be careful about making sure that one of my answers is not positive or negative 2. That's the whole point of that. So let's go on. Next, I would take the entire equation. Oops, something happened to my negative 1 here. I must have deleted it by accident. I'm going to take the entire equation and multiply by this common denominator, x plus 2 times x minus 2. And so that's going to give me technically 12. Notice both of these expressions, when multiplied by my common denominator, both of these factors are going to cancel off. So I just have 12 times 1. In the second piece, I have negative 3 times, the only expression that would be left is the x plus 2, because the x minus 2 would cancel off. All right, this x minus 2 here goes away with that x minus 2. And then I have negative 1 times both of the factors, x plus 2 and x minus 2. All right? Now note, we know that x plus 2, x minus 2 is x squared plus or minus 4, because that's where we got those two factors from. So this is x squared minus 4. So really what's going to happen is I'm just going to multiply the negative 1 times x squared minus 4. All right? All right, so if I just try to clean this up a little bit, I've got 12 minus 3x minus 6 equals what is going to be negative x squared plus 4. Again, the negative 1 gets multiplied into that factor. All right? And now I'm back to a quadratic equation. All my fractions are gone, so let's clean it up. I'm going to move everything to the right or to the left side to keep the x squared positive. So x squared minus 3x, 12 minus 6 is 6, and then minus 4 again is 2. So all of that equals 0. X squared minus 3x plus 2. That's a much easier expression to factor than the one we had above. We got x and 2 and 1. If they're both negative, then it works. And so preliminary answer here would be that x equals positive 1 and x equals positive 2. But the problem is x is not allowed to be positive 2 based on our domain restriction. And this lies the problem with rational expressions. The reason why we had to find the domain up here is because we can sometimes end up with extraneous answers. So that 2 has to be thrown out. Our only answer here is x equals 1. All right? You might be asking yourself, why in the world is this part of chapter 7? It has nothing to do with the systems that we were solving. And you're right, so far it doesn't. We're going to find a way to connect this in a moment. All right? So this was review. This was actually stuff that would have been studied way back in like chapter P, the beginning of the year, or even chapter 1. So it's been quite a while, but you've done it before. It can sometimes be tough, that's for sure, I'm not going to lie. But thankfully, most of the work that we're doing is going to keep it pretty simple. All right, let's move on. All right, given a rational expression, the process of finding the fractions that were added or subtracted in order to obtain the expression that you're given is called partial fraction decomposition. Big words, long phrasing, partial fraction decomposition, to say that basically what we're doing is we are taking fractions like this, and we are breaking them apart into smaller fractions. So we're going to take something like this 5x plus 7 and break it, 5x plus 7 over x squared plus x minus 20, and break it apart into something like this. only it won't be an equation. It would be just an expression, something like this. Break it apart into smaller fractions. All right, that's our goal. There are a couple of different techniques here. They vary just slightly depending on the type of factors that you have in the denominator. So it all has to do with what is left on the bottom. What kind of scenario are you dealing with in the denominator? Are they linear factors? Are they quadratic factors? Are they distinct, meaning it only shows up in one position? Or do they repeat? Do you see them showing up in multiple positions? Or I should say, are those factors counted multiple times? All right. So really, it has everything to do with that denominator. Our job is to first try to factor and analyze the denominator. All right. A little history lesson. This is John Bernoulli. There were two Bernoulli brothers, actually, and they both did many, many things in the realm of mathematics. As you can see, back 1667, 1748 was John. They were Swiss. John was a Swiss mathematician. He introduced the method of partial fractions, was instrumental in the early development of calculus. Bernoulli was a professor at the University of Basel, and he taught most famously Leonhard Euler. We just got done dealing with, actually no, it was a while ago, but we dealt with Euler's number, the number E, approximately 2.718. So anyway, John Bernoulli was his teacher. All right, so we are tasked with trying to break this fraction apart into smaller pieces. So here is our job. First off, let me say that there are two methods for doing this. Two methods. And I'm going to actually, on this first example, I'm going to show you one of them. I'm going to show you both of them, but I believe one of them is easier than the other. And so for the other examples, I'm going to use pretty much just one method. First method, and the easiest one, is a method we call inspection. This is the one that we're going to focus our attention on the most. Second method, which is the method that my math lab would show, is called equating coefficients. Whoops, didn't mean to do that, sorry. Equating coefficients. Inspection is the easiest one. Like I said, that's where we want to be focusing our attention. That's the method that's going to be the quickest route to your answers. All right, so the first thing we have to do is factor the denominator. So we've got our 5x plus 7 broken apart. When it breaks apart, it's going to break apart into x, and notice the factors of 20 are 20 and 1, 10 and 2, 5 and 4. I'm going to use 5 and 4 because if I let the 5 be positive and the 4 be negative, then when I multiply this out, I will get back to x squared plus x minus 20. All right, now here's the concept. So that's easy. You guys should know how to factor by this point. You should be able to do that. This is the new part. This is the part you have never learned. This is the part you've probably never seen. When breaking apart a fraction like this, it will, without a doubt, be able to break apart into some constant divided by x plus 5 plus some other constant divided by x minus 4. And by some constant, I mean some just number, any number, 5, negative 7, 24, any number. So some number, we'll call that number capital A, divided by x plus 5, plus some number, we'll call it capital B, divided by x minus 4. All right? Our job, our focus here is on A and B. We have to try to find what A and B are so that we can legitimately say that 5x plus 7 over x plus 5 times x minus 4, or 5x plus 7 over x squared minus x minus 20, is able to break apart into this fraction with whatever A is, plus this fraction with whatever B is. That's our job. All right, so let's get to it. Based on what we just did in these problems, I want to try to solve these equations. So I'm going to take the whole equation, and multiply by the common denominator. X plus 5 times x minus 4. That leaves me with, on the left, it will always leave me with 5x plus 7, the numerator. It'll leave me with just the numerator because these two factors, when I multiply by this, both factors will cancel. On the right, I'm left with a times the x plus 5 cancels, and so I'm only left with x minus 4. And then b times, notice the x minus 4 will cancel, and so I'm left with only x plus 5. And so I've essentially deleted out all of my fractions. And I've got a simple expression here. It's got three variables. It's got an x, it's got an a, and it's got a b. I don't have any way to solve this yet, or at least I should say you don't have, right? This is where our two methods come in. The first method is called inspection. I'm going to split my screen here, and I'm going to show you both. All right, this first one is inspection. All right. What we do to solve by inspection is we begin by choosing numbers to plug in for x that will simplify this equation for us. Again, you want to just, out of thin air, you're just going to inspect the equation, inspect this equation that we're dealing with. This is where we are. Just go, okay, I can make this equation a lot simpler if I just let x be, let's let x be anything I want. Anything. You can let it be 0. That makes it easy. That gets rid of this. It gets rid of this. That gets rid of this. You can let it be 1. That could simplify things. You can let it be -1. There's no need to let it be, 1002.734. That would be ridiculous. Just choose numbers that make it simple. Obviously, the simplest numbers that most people would think of are 0 and 1. You're going to let x be some value. But I've got something even better. What if we let x equal +4 and -5? So see what happens if I let x be +4 and -5. All right? If x is +4, if I plug in +4, then I get 5 times 4 plus 7 equals a times 4 minus 4 plus b times, that should be like that, 4 minus 4. b times 4 plus 5. If I'm letting x be 4, then the equation above, this equation here, will turn into what I've got written here on the last line. Will turn into this. If I simplify that, that gives me 27 is equal to, notice what happens to the a. This is why I'm letting x be 4. If I let x be 4, then I'm multiplying by 0 and the a disappears. So I'm left with just 9b. 5 plus 4 is 9, and 9 times b is 9b. Which means when I divide, b must be 3. And I have found the value for the numerator. If I let x be -5, then I'm going to get 5 times -5 plus 7 is equal to a times -5 minus 4 plus b times -5 plus 5 And of course, you can see where I'm getting with this. If I let x be -5, then I end up with -25 plus 7, which is, of course, -18. Careful with your algebra there. On the left, I get -9. Sorry, on the right, I get -9a, and then the b's disappear, right? Because just like what happened here, the a's went away. That's going to happen here. -5 and 5, right? -5 and 5 is 0, and the b's go away. So I have -18 equals -9a, which means when I divide by -9, a must be 2. So our final answer is that 5x plus 7 over x squared plus x minus 20 is really the same as 2 over x plus 5 plus 3 over x minus 4. And I guarantee you, if you go back and you multiply these by a common denominator, meaning you take this expression, you multiply by x minus 4 over x minus 4, and you take this expression, you multiply by x plus 5 over x plus 5, and you combine them, you're going to get back to where we started. You're going to get here. All right? There we go. We have successfully broken down this fraction, 5x plus 7 over x squared plus x minus 20. All right? I'm going to show you, not in full, but I'm going to show you partially anyway, the equating coefficients method, the second strategy that's listed here. All right, equating coefficients. All right, this strategy says you're not going to just choose numbers and let x be anything anything you want out of the sky. We of course weren't choosing them at random. We were selecting values that would make these expressions equal 0. That's why we chose 4 and -5, because 4 made that 0 and -5 made that 0. But you're not just choosing values to let x be. What you're going to do is you're literally going to simplify the equation that you're given here, the one that I've highlighted in orange. You're going to, left side is leave it alone. Left side is just 5x plus 7. The right side is technically ax minus 4a, plus bx plus 5b. So I'm multiplying by the a and the b. I'm simplifying the right side. All right, now I'm going to group together the terms with x and the terms without x. So there's an ax plus bx, and then there's a minus 4a and 5b. Sorry, 5b. So if I've grouped these together, now these two terms have x, and these two terms are just a constant. All right, these are with x, and this is constant. Oops. And now, I'm going to literally write with x. There we go. Now, if you compare the right side of this equation, this is the key. You're equating coefficients. If you compare the right side with the left side, the term on the right here that I say with x is technically, if I factor an x out, it's x times a plus b, right? If I factor out of this the x, I'm left with a plus b. So this really coincides. This is where the equating comes in. This a plus b is attached to an x, and it is set in an equation where on the left side you've got a value attached to an x. So in other words, what we're saying is that 5 must be the a plus b. 5 must equal a plus b. Because the only way the left side of the equation can equal the right side of the equation is if the stuff that's attached to the x on the right is the same as the stuff that's attached to the x on the left. So the a plus b that's attached to the x on the right must be equal to the 5 that's attached to the x on the left. They have to be equated. They have to be true if this is an equation. So 5 equals a plus b. Well, and the same is true about our constant. The constant term on the right has to be equal to the constant term on the left. It's gotta be true. This constant must be equal to this, which means 7 is equal to negative 4a plus 5b. And what have we done? We have created a system of equations. And the system of equations is very much like the systems of equations you were solving in section 7.1 and 7.2. So you could use your methods for solving systems. You could use a calculator, for crying out loud. You could just set up a matrix equation and solve it on a calculator using RREF if you wanted. But if you solve the system, you're going to find that A equals 2 and B equals 3. The same answer we got here. So this method of equating coefficients, which requires a little bit of extra factoring and extra breaking down, this method is also legit. It is usable. If you don't like my inspection method over here, you don't have to use it. You can use the equating coefficient style. But I'm going to say that most people use this. They don't show as much work as I did on this inspection method. It's definitely easier to do. I highly recommend it. All right, let's move on. Number 4, we've only got 2 more, but they can get a little meaty. So, number 4 says decompose 6x cubed plus 5x minus 7. I'm going to tell you right now, I think this problem works out better if we make an adjustment to it. So I have to get this word out to everybody who's doing this problem. But really, I'm going to say let's insert in here a negative x squared factor. All right, so in other words, I think this problem was written wrong. It's printed wrong in the notes. I'm going to say let's rewrite it as 6x cubed minus x squared plus 5x minus 7. Makes it a lot easier to work. All right? Okay. Here's the trick with this one. Remember, we go back up. The first thing we had to do was factor. We factored this into x plus 4, x plus 5, x minus 4. We are going to do that here also, but the problem is this fraction is improper. It is an improper fraction. We have to handle improper fractions differently. In fact, I like that. Improper. It's an improper fraction. We need to divide first. We need to break this thing down. If it's an improper fraction, how do I know it's an improper fraction? Because the numerator has a higher degree than the denominator. If the numerator has a higher degree, then you need to start out with division. And this is long division. So we're going all the way into the tool bag and pulling out some tools that we haven't talked about for quite a while. But I am literally going to divide 3x squared minus 2x minus 1 into 6x cubed. Remember, I inserted this other term here, minus x squared plus 5x minus 7. Again, if you missed that, I put this negative x squared in here because I think that this problem works out easier if this top expression has negative x squared inside. I'm literally changing the problem. All right. Okay, so if we do this long division, first thing we have to do is consider what do we need to multiply 3x squared by in order to get 6x cubed, or you could say 6x cubed divided by 3x squared gives you what? What's left over? 2x. 2x, when multiplied into 3x squared, gives me 6x cubed. So I'm going to take that 2x and I'm going to multiply it into each term, and I'm going to lay it out underneath here. So that gives me 6x cubed minus 4x squared minus 2x. And then I have to subtract that. And when I subtract, the 6x cubes go away, and I got what turns into addition of the opposite. All right, so 3x squared plus 7x, and then I'm going to pull down this minus 7. All right, and I start the process over again. Notice that 3x squared already matches the 3x squared, so I'm just going to divide and get 1. And that's the next term of my answer, 2x plus 1. And then I multiply it back in, and I get 3x squared minus 4x. I'm sorry, I'm multiplying by the wrong thing. 3x squared minus 2x minus 1. And then I have to subtract that. And it leaves me with 7x plus 2x is 9x. And then negative 7 plus 1 is negative 6. All right. Whew. So we divide, and our answer is 2x plus 1 plus 9x minus 6 over the divisor was 3x squared minus 2x minus 1. Okay? So we've taken our original expression and we've divided and we've broken it down. Now our job is to break apart this. This is what we are going to use partial fraction decomposition on. All right, so we're going to break down this remainder. Again, what have we said so far in this problem? If your problem is an improper fraction, meaning the degree of the numerator is higher than the degree of the denominator, or equal to, if the degrees are equal, you have to divide first. You start out with division, and then you use your partial fraction decomposition on just the remainder in the problem, not the first part. This is already broken apart. This is already as simple as it gets, 2x plus 1. But here we have to do our partial fractions on. All right, notice that the one we started with up here, the numerator had a degree that was smaller than the bottom. So this was already a proper fraction, and we went straight into our partial fraction work. All right, but on this one, we can't do partial fractions until we get this into a proper fraction. Numerator is x, denominator is x squared. Now it's a proper fraction. So let's get to work. This remainder, if it breaks apart into partial fractions, which it will, then it's going to break apart into, let's factor the denominator. It's got to be x and x, 1 and 1, and the only factors of 3 are 3 and 1, right? They got to go here and here. So 3 and 1. So now it's just a matter of the signs. Well, I have a negative 2x in the middle, which means the negative must be with the factor that gets multiplied by 3, and so that's going to be here, and that's a plus. All right, you multiply this back out, I guarantee you 3x plus 1 times x minus 1 is the same as this. All right, so 9x minus 6 over 3x plus 1 times x minus 1 is going to break apart into two fractions because we have two factors, some constant over 3x plus 1 and some constant over what is technically x minus 1. All right, so some constant a plus some constant b. And now our job is to find a and b. All right, so now we multiply. I'm going to take the whole thing and multiply, let's say, by the denominator is 3x plus 1 and x minus 1. So if I multiply by this, the left side leaves me with just 9x minus 6. The right side is going to be a times x minus 1 because the 3x plus 1 gets canceled off. Right? Gets canceled off. And then b times 3x plus 1 because the x minus 1 cancels off here. one of the common mistakes I see with students is that they will write it as a times 3x plus 1 and b times x minus 1. They'll put the wrong factor on that variable. So be careful. 3x plus 1's cancel, and a gets stuck with x minus 1. The x minus 1 cancels, and b gets stuck with 3x plus 1. All right? Let's keep rolling here. So by inspection, I'm going to say let x be positive 1, because positive 1 makes this expression 0, and negative 1/3, because negative 1/3 makes this expression 0. So if x is positive 1 and negative 1/3, now I get to work. If x is positive 1, then I'm going to get, on the left side, 9 minus 6, right? 9 times 1 minus 6, which is just, let me try to make this simpler. 9 times 1 minus 6 is just 3. On the left side, I get 3. On the right side, if x is 1, this expression with the a cancels. Again, all of our attention now, once we've got it so there are no fractions, all of our attention is on this equation. We're working with this equation. The a times x minus 1 cancels off, and I'm left with b times what is really 4, so 4b. Right? It's 4 because x is 1 and 3 times 1 is 3, plus 1 is 4. So what I just found is that b must be 3/4. 3/4. Then, if I let x be 1/3, negative 1/3, be careful, negative 1/3. Oops. If x is negative 1/3, you might need to take a moment and do this in step instead of just trying to throw values in mentally. I am multiplying by negative 1/3. On the left side, every x is going to be negative 1/3, right? I've got a negative 1/3 plugged in here for x. Oops. And then notice, if x is negative 1/3, this factor disappears. This factor becomes 0, and so this term, b times 0, is gone, so I don't need it. So when I'm plugging negative 1/3 into this equation, the left side, I get negative 1/3 times 9, and on the right side, I've got what is technically negative 4/3 here times a. All right? So 1/3 of 9 is, what's negative 1/3 of 9 is 3, and then I'm subtracting 6 more, so I've got negative 9. That's what the left side becomes, negative 9. And the right side is negative 4/3 a. Negative 1 minus, I'm sorry, negative 1/3 minus 1 is negative 4/3, times a is negative 4/3 a. So now if I solve for a, I'm going to multiply by 3/4. A is equal to positive 27/4. 27/4. So now I have my a and b, which means my original expression is technically, here we go, 2x plus 1 plus a over 3x plus 1 and b over x minus 1. A, we just said, was 27/4, and b was 3/4. All right, here's the problem. My math lab is not going to accept that. That's too messy. My math lab's like, don't think so. Let's be a little bit more clear with your answer. So you have to write this in a better way. You can't keep a fraction over a fraction or a fraction in a fraction. It's not allowed. So instead, the answer would be 2x plus 1. We're not messing with that. But this expression gets rewritten as 27 over the 4 jumps into the denominator with the 3x plus 1. We don't have to multiply it, but we just move it down. And then this expression, the 4 jumps down. We have 3 over 4 times x minus 1. This is the answer that would be acceptable on my math lab. They didn't take it. There we go. All right, that's the only thing that would be accepted here. All right, there's a lot to that problem. Pretty meaty. Hopefully it made sense to you. Let's move on.